let's integrate this inequality from what do you call 0 to capital T. So if you're going to integrate this inequality from 0 to capital T, 0 to capital T, so you're going to get what? So this will go away and you're going to get u of t square minus u of naught square, okay, plus nu integral from 0 to t and u of t square dt and 1 over mu and the integral from 0 to t and f of t square v prime. Okay, I can send everything on other side, okay, and I can rewrite this inequality as 0 to t u of t square dt, and this is, say for example, less than or equal to a constant k1, okay, so it depends on a constant k1, where the constant k1 depends on what? It depends on this, okay, norm, it depends on, and this is finite actually, so if you integrate, I mean if you see the definition of what do you call f, so the f was chosen from L2, 0 to t, v prime actually. Okay, so this guy is a finite number. I can send all of this stuff on other side and I can call it a constant actually, and this constant I can say that it depends on what? It depends on u naught, it depends on f, it depends on nu, because this constant is going to appear, and it depends on what you call the capital T. Okay, so I can say that for any capital T, the u of t in V norm is a square integrable actually, because and this estimate is true kind of uniformly. Okay, so this is one of the crucial estimate. Let me put it in a colored box. Okay, what is the next thing? Now let's integrate the same inequality, okay, this inequality number 2, not from 0 to t but from 0 to a side. Okay, so integrate 2 from 0 to an s, where s is a number in the interval 0 to t. Okay, so when you're going to do it, what you're going to get by integrating, so you're going to get u of s square, that can be estimated by u naught of square of square plus integral from 1 over nu. Okay, I can do one of a thing actually before integrating it. Okay, so this inequality is interesting. Since both of these terms are non-negative and this is less than or equal to this, so I can say that each one of this term is also less than or equal to this. So even if I So what I'm doing basically is that first I'm dropping this term, so the inequality still holds, and then I'm integrating this inequality, you know, by dropping this term, and then I'm integrating it before from 0 to s. So you're going to get 0 to s, and say f of t square its norm in v prime and dt. Okay, and what we can say. So now I can say that since this u square is true, like this is true for all s in the interval 0 to t, so this would be also true for the supremum actually of u of s square, where s is between, what do you call, 0 to t. So s in the interval 0 to t, and let's call everything on this side as k2. So now k2 is what? So the k2 is something that depends on u naught again, f, nu, and capital T. So it depends on k2. Okay? So this is another important inequality. Let me point this out. This inequality is telling you that u, so every u that satisfies Navier-Stokes equation in weak sense also satisfies, what do you call, is a square integrable with values in v, because this is v norm actually, uniformly. And this shows that that u belongs to, what do you call, L infinity with values in h actually. Okay, with values in h, because we are talking about the h now. So you have to keep track of the things and, you know, keep track of the analysis actually. All right. So these two are the first kind of a priori estimates actually. So we obtained these a priori estimates by replacing the v by the u of t. So now what I would like to do, I would like to now replace, in the same star, I want to replace v by au. Okay. So let's do the calculation, and let's replace everywhere in this equation, replace v by au of t, where a is your Stokes operator. And as I'm saying that while doing these calculations, there is no specification of domain, so these calculations are valid for periodic domain and full domain, full space, and bounded domain, and they are also true in 2 and 3 dimensions actually. And also in n dimension. Okay. So if I'm going to do this, what I'm going to get, I'm going to get u prime of t au. I'm going to get nu u of t au. Okay. But this double norm. I'm going to get b u of t au of t, and I'm going to get f of t and au of t. So this is what the terms I'm going to get. Now you need to keep in view the result that, as I said, what was the key? One of the key expression, that if you have AUV, so recall, so we used it also, recalled that AUV is equal to this double norm, double inner product UV for all UV and V actually. So this is true for all UV and V. So keeping in view this relationship, what would be the impact of this on this actually? So the impact of this on this is going to be so from the first term I can pull the time derivative out, okay, the time derivative out. So okay, but there are reasons that I'm allowed to, why I'm allowed to do it, and I hope that you know it very well by now. So I can pull the time derivative outside now, and I'm going to get UAU. But UAU is the gradient of U square actually. And the gradient of U square is basically V norm. Okay, so it's going to be the V norm square of the U. Okay. So the first term, pull out the derivative, you're going to remain with U of t AU, which is going to be V norm of square U. So let's get d by dt of U of t squared V norm plus, what would be the next thing? This is by this definition. So if I have UV here, so it's AUV, so this will also become, so if I apply this definition here, so this will become what by this definition? So this will become AU, inner product AU in H sense actually. So AU. So if it is AU, so this is going to be mu and A U of t square actually. Okay, so you're going to get A U of t square. And what would be, so I need to keep this B U of t, U of t, V of t as it is, and all this is equal to, what do you call, f of t, okay, so f of t AU of t. Okay, f of t AU of t actually. So this is what you're going to get as an outcome. Now, let's recall we have some estimates for say BUV phi. So in this equation, if I substitute U, U and U, then you know what you're going to get. You're going to get an expression. So in this inequality, that is true for small b, if I substitute U, U and AU, so I'm going to get, you know, H norm of AU, and all these are going to be U's actually. So in simplified version, simplified manner, by the way, I can do one of a thing first, that I can estimate this guy as previously as mu by 4 AU of t square. So I can do the same Holder's inequality and then Young's inequality, AU of t square and 1 of mu f of t square actually. Okay, so this is what that you're going to get. Now we are in the interesting situation actually. So this inequality, let's call this inequality as say inequality number 4. this inequality is true in general. Now I'm gonna get into the particular dimension. I can't go more, with this. So now let us consider the dimension 2. By the way, this inequality let's say that this inequality is valid only in dimension 2. So for dimension 3 you have some other versions of this inequality. So since I am in dimension 2, so I can use this inequality for u to be, so by replacing v and w by u and v of t, not v of t, I think it is au of t. Okay. So this is au of t. au of t. Okay. All right. So where were we? So we were here. So we kind of derived this inequality, and now I'm gonna use my estimate from here. Okay. This inequality, which is valid in 2 dimensions. If I apply this inequality here, I'm gonna get something like this actually. Okay. So I'm leaving this for you to figure it out. That how that this works actually. Okay. So in n equal to 2, applying that inequality, I'm just directly writing the result. So you have to carefully think about it for yourself. So du by dt is square plus 3 over 2 nu and a u of t square in h norm and what? And 2 over, okay, so 2 over, by the way, how did you got this 3 over 2? So I took this and subtracted from here, so I have 1 minus 1/4 actually. So 1 minus 1/4 will become 3/4. Okay, so I have a 1 over 2 here. Yes, I have a 1 over 2 here. Yes. So if you have a 1 over 2 here, so you multiply this inequality with 2, so this will become what you call 3/2, and this will become 2 by mu, and using this estimate I can have what you call 2 times of C2, C2 is some constant, and u of t 1/2 and a u of t 3/2 times u of t. So this is what that's going to get at. Now I can, so 2 over mu, that's right, 2 over mu and f of t square mu norm actually. So if I again apply, say, Young's inequality a bit cleverly, okay, you have to figure this out for yourself. Okay, then I can majorize this side or dominate this side by this actually. So I'm going to get 2 over mu f of t square. It's a simple application of what do you call this simple application of what do you call again the Young's inequality, and you're going to get an expression like this: mu over 2 a u of t square plus you're going to have some constant c1 prime, okay, I have some constants, let's call it c1 prime, and u of t times norm of u of t square actually. Okay, so this is what that I'm doing. So you have to figure it out that how Young's inequality can lead you to this expression. It's not difficult. You know, I think these two terms need to be put together, and you have to choose constants cleverly that you can get to such an expression actually. So you get this, and once you get this, so you have even more simplification of this term. So take this nu over 2 and subtract it from here, so you're going to get only nu a u of t square. You have to keep this in view that what the calculation that we are doing are now true in 2 dimensions. This is true in general, but you know, all this stuff is true in 2 dimension actually. So what you're going to get, so if you take this and you know subtract it from here, so finally you're going to get d by dt of u of t square. Shall I write? Okay, so I mean you can read it from the book actually. The version of Young inequality that here is being used looks like this. So it's not the simple Young inequality, but it's this Young inequality. So AB is less than epsilon times a power p plus what do you call c epsilon, some constant depending on epsilon, b q. Okay, and epsilon is a positive number. Epsilon is a positive number, and q is as obviously p over p minus 1, and c epsilon can be explicitly written as p power minus 1, p minus 1, p power q, and epsilon power 1 over p minus 1. So there are different versions of what you call Young's inequality, and you are applying this Young inequality for p equal to, okay, so to obtain this from here to go here, I'm applying the Young's inequality with p equal to, what do you call, 4 by 3, okay, and epsilon equal to nu by 2. Okay, so epsilon equal to nu by 2. And obviously I am taking the product of this and this as A, and AU of t as B actually. Okay, AU of t as B. Yeah, no, like this entire term as B. And then applying this inequality, I get such kind of a result after this. Okay, so I'm just writing explicitly for those people who are watching this video actually. Okay? Alright. So what did you get? So if I simplify it, so you're gonna get plus nu a u of t square, okay, less than or equal to 2 by nu f of t square plus c1 prime u of t square, okay, u of t square and norm of u of t power 4. Okay. Power 4. I think it must be not a square here, but power 4. So this is what finally you get as an inequality. Let's give this inequality a name. I know these are a bit messier calculation. These things you can read it for yourself, but I'm just going through these calculations so that when you read it for yourself, you will have already some sketch in your head actually. Okay. So what is the next thing? So we got, first we did the stuff with u, and now we are doing with AU, and I'm getting reaching to such kind of an inequality. What? By the way, if you see, each one of the term in this inequality is non-negative actually. So I can say that if the sum of these two things is less than or equal to this, the inequality would still hold if I drop this term. So assume that I dropped this term actually. So if I drop this term, then I can put the remaining inequality in the form of a differential inequality. That goes like y prime less than or equal to a plus theta y. Okay? A plus theta y. Where y of t, okay, y of t is u of t square, okay, and a of t is 2 over nu f of t square, okay, and the theta of t is c1 prime u of t square and log of u of t power 4. So this is what you're gonna get actually. Okay? Alright. Now I'm gonna apply the following version of the Grunwald lemma. Okay, so I'm going to apply the following version of Grunwald lemma. Okay. And the Grunwald lemma says that if you have a situation like d by dt of y of t exponential